This is Biomaterials Lecture 16, Video 2. I hope this video gave you a basic idea of the complicated and fascinating processes that occur in the human body when it heals. So, our bodies are capable of healing. Unfortunately, there are times when a laceration is so severe that the body cannot heal itself and needs some assistance. The Cleveland Clinic has provided some guidelines for seeking emergency help when a laceration has occurred. Damage to the skin needs medical attention when it is deep enough to expose the dermis or gaping open that gentle pressure cannot easily close the wound. In such cases, the body needs additional help to close and heal the wound. You exist because your ancestors did not receive such deep lacerations prior to creating their children. Receiving a laceration that needs medical attention today was likely a death sentence for early humans. Lacerations that can't heal result in infections, illnesses, and subsequently death. Think about people who do not exist today because some cave person cut their foot while walking around and died from infection. You are a wonderful impossibility. A solution to lacerations was developed about 5,000 years ago when Egyptians first started experimenting on medical treatments. Analysis of mummies showed that techniques for closing wounds with sutures were being used at that time. A suture is any strand of material used to bring tissues together or tie blood vessels. The primary purpose of a suture is to bring tissues close together to facilitate healing in a minimum amount of time while minimizing scarring and other complications. Ideally, a suture will retain its strength until a wound heals sufficiently to carry the load on its own. One technique of using sutures is shown here, while an actual image of a suture is shown to the right. Sutures can be classified as natural or synthetic, and absorbable and non-absorbable. Non-absorbable means that the suture can maintain its strength over a time period of over 60 days. The first sutures were both natural and non-absorbable. For centuries, natural materials like cotton, linen, silk, and strands of horsehair were used to approximate wounds. The first natural and absorbable sutures were developed in the 2nd century. Absorbable sutures can undergo rapid deterioration and lose their strength within 60 days. Catgut was the first biological material used as a suture. Although it's called catgut, the suture is typically made out of the intestines of horses or sheep. The manufacturing process for catgut is similar to the process used to make strings for violins and guitars. Although some of you may be hearing the word catgut for the first time, you should now all be aware of its structure. Surgical catgut is composed of 98% pure ribbons of collagen. Recall the hierarchical structure of collagen fibers, which can be broken down to collagen fibrils, which are bundles of triple helices of collagen molecules that are each a chain of amino acids in an alpha helix. In our discussion of tendons, we discussed the strength of these hierarchical collagen structures. If you'd like to review our discussion on collagen, a link to the relevant lecture is provided in the description below. The bottom line is that catgut is made out of collagen. It is relatively strong because of its hierarchical structure, and it experiences degradation over time. Once implanted into the body, catgut sutures can be degraded by enzyme catalyzed degradation, which we discussed in the previous lecture. Recall that enzymes are proteins that are present in the tissue and fluid surrounding a biomedical implant. These enzymes have an affinity for certain chemical groups and polymers and can cause either hydrolytic cleavage or oxidative degeneration in these polymers. Well, catgut, which is made out of the intestines of sheep or horses, has chemical groups that are susceptible to enzymes that humans produce. In the previous lecture, we not only discussed enzymatic attack, but we also discussed sterilization. In the 1800s, it dawned on people that sterilizing a suture made from animal intestines is actually a good idea. So in the mid-1860s, Sir Joseph Lister devised a technique for sterilizing catgut, which most definitely saved a tremendous number of lives. So at the very least, sutures should be sterile and bring lacerated tissues together. But what are other desirable properties of sutures? Well, a high uniform tensile strength is certainly desirable. However, ideal sutures don't have to be much stronger than the tissues they are bringing together. The ideal suture should also be able to retain its high tensile strength after it is implanted into the patient for the amount of time needed. This is because sutures need to hold the wound securely throughout the critical healing period. Ideally, a suture should not have to be removed because this carries with it the risk of infection and injury. Therefore, sutures should be rapidly absorbed once they have served their purpose. The ideal suture disappears after the patient is healed. Sutures should also have a consistent, uniform diameter. And of course, sutures should be sterile. Furthermore, the ideal suture should be pliable to enable the suture patterns and knots like the ones shown on this slide to be formed. Finally, the ideal suture should not have irritating substances or impurities, and it needs to have a predictable performance. Of course, sutures cannot be implanted into people without surgical needles. Surgical needles are curved in shape and can have varying length and diameter. Swaged needles are manufactured with a predetermined length of suture thread attached to its sharpened tip. This eliminates the need to tie sutures to needles, and it minimizes injury during suturing. The ideal surgical needle should be first and foremost sterile, but also made of a metal that is resistant to corrosion. In order to minimize trauma to a patient, needles should be as slim and as sharp as possible, stable, and capable of carrying sutures through tissue. The mechanical properties of the needle are important because it needs to be rigid enough to resist bending, but not too brittle that it breaks in the patient. This slide shows various methods of using sutures to close a wound. Again, it is important to remember that the purpose of a suture is to secure an edge-to-edge seamless seal to give a previously open wound the means and time to heal itself. Absorbable sutures are particularly useful for repairing deep wounds that extend below the epidermis. For such extreme injuries, the use of a suture that can be dissolved and absorbed by the body is preferred. Imagine that a wound deep in the body is repaired by suturing. If a suture were not absorbable, then an additional surgery would be necessary to remove the foreign object from the body, which carries with it a risk of infection and further injury on top of another surgery. Absorbable sutures have an immense benefit when it comes to repairing deep wounds. So catgut sutures have saved an immeasurable number of lives since they were first used, and they continue to be used today. However, these natural absorbable sutures have a number of drawbacks. Natural absorbable sutures are broken down by enzymes, and people produce different amounts of enzymes. Furthermore, catgut is a biological material, and it is a challenge to ensure consistency in the intestines of sheep and horses. Therefore, a significant drawback with catgut sutures is their unpredictable rates of degradation. Modern catgut sutures can typically maintain their strength for several days after implantation and absorb completely in 70 days. However, there may be some situations where suture strength needs to be maintained for longer periods of time. For these situations, catgut is not ideal. Work has been done to improve catgut sutures, and chromic catgut is capable of maintaining its tensile strength up to 2 weeks after implantation. Chromic catgut is obtained through a treatment with a chromium salt solution, and it is typically absorbed within 3 months after implantation. Despite the improvements in catgut technology, the natural material carries the additional risk of giving patients mad cow disease, which is why the suture is banned in Europe and in Japan. So, how do Japanese and European people close their lacerations? Thankfully, absorbable synthetic sutures were developed several decades ago and are widely in use. The first absorbable sutures were made out of a polyvinyl alcohol-based material, and around the same time, radiation caught on as a better means of sterilization. By the 1960s, dissolvable sutures made out of polyglycolic acid were invented and became universal throughout most surgeries. Absorbable synthetic sutures are now widely used, which is why it is important to understand their structure, properties, and performance. The good news is that there is not much to memorize when it comes to absorbable sutures that have been approved by the US Food and Drug Administration. There are actually only 3. The first is polylactic acid, or PLA. It is a semi-crystalline polymer with the repeat unit shown here. It has a tensile strength of 4.8 gigapascals. As mentioned earlier, polyglycolic acid, or PGA, is also used as a synthetic absorbable suture. It has a tensile strength of 12.5 gigapascals and has the repeat unit shown here. Note the key difference between PLA and PGA. One has CH3 as a side group and the other just has H. The third absorbable synthetic suture approved by the FDA is actually a copolymer of PLA and PGA. It is called PLGA, and its repeat unit is the PLA repeat unit bonded to the PGA repeat unit. This copolymer is also called Vicryl. The goal of a biodegradable polymer is to produce low molecular weight products that are both water soluble and safe for the human body. The human body should also be able to clear these low molecular weight products by natural processes. Recall that natural absorbable sutures are broken down by the enzymes in the human body. For synthetic absorbable sutures, the breakdown of polymer chains occurs through hydrolytic cleavage. Thus, the water in the human body breaks apart synthetic sutures. In the previous lecture, we discussed how the hydrolytic cleavage of water works. First, water dissociates into a hydroxyl ion and hydrogen. The hydroxyl group attaches to one monomer, and the hydrogen attaches to another monomer. The cleavage of PLA by hydrolysis is shown in this slide. The hydrolytic cleavage of PLA results in the formation of lactic acid, which is metabolized by the human body. Lactic acid is indicated by the green dashed box on this slide. Here's another example. Take a look at how PLGA is broken down into lactic acid and glycolic acid. Both lactic acid and glycolic acid can be metabolized by the body. So PLGA is not only a biocompatible material, but the products formed during its degradation can be removed by the human body. Recall that the natural absorbable sutures get absorbed within 90 days and maintain their strength for 2 weeks at the most. Furthermore, the performance of natural absorbable sutures is a challenge to predict because the levels of enzymes change from patient to patient. Synthetic absorbable sutures have predictable mechanical properties when they are implanted into the human body and can retain their strength for longer periods of time. For example, PGA can retain its strength for 12 weeks, while PLA degrades over a period of 5 years. PLGA has a tensile strength that decreases by a rate of 25% per week after 2 weeks and is absorbed between 56 and 70 days. Now that you're familiar with natural and synthetic absorbable sutures, we can now discuss the surface degradation and bulk degradation of polymers. When it comes to absorbable sutures, surface degradation is desirable. Here's why. Surface degradation occurs when the rate of water penetration into the material is less than the rate of polymer hydrolysis. In other words, hydrolysis happens at the surface of the polymer instead of inside it. This means that the polymer will decrease in thickness but will maintain much of its integrity during degradation. If you take a look at this very simple sketch of surface erosion, you can see that the hydrolysis reactions are only occurring at the surface of the polymer, and its internal regions are untouched by water until they are uncovered by the surface erosion. In contrast, bulk degradation occurs when the rate of water ingress into the polymer is greater than the rate at which the polymer is converted into its water-soluble degradation products. If water can penetrate the interior of the polymer, then hydrolysis and swelling and dissolution can occur inside of the polymer, which will weaken it. Polymers that experience this type of degradation will experience a rapid decrease in their mechanical properties, which limits their use in load-bearing applications. Polymers that experience bulk degradation will develop cracks and fissures before they completely degrade, which is undesirable when it comes to wound healing. Let's apply what we've learned. Take a look at figures A and B and the stress versus strain graphs labeled 1 and 2. Which of the statements shown here is correct? Please click on the link below to complete this in-video question and receive credit for your work. This is an open book, open note assignment. You may take as much time as you need, but the important things to remember in these in-video assignments are that you do not ever hit the back button on the form and you complete the questions before starting Lecture 16, Video 3. We trust you to follow the honor code. We will go over the solutions to this problem in Lecture 16, Video 3, which is also linked below.